Fluids used in mechanical systems come in many different types. The type of fluid chosen for a particular application depends on its characteristics. One of the most important characteristics of a fluid is its viscosity. Viscosity is defined as a fluid's resistance to flow. Fluids with low viscosity flow very easily. Water is a type of fluid with low viscosity. Fluids with high viscosity are more resistant to flow. Honey is a type of fluid with a high viscosity. Therefore, honey is more viscous than water. Another characteristic of fluids is the viscosity index. This rating relates the flow of a fluid with its temperature. Many fluids begin to flow more easily as temperature increases. The viscosity index is the measurement of this characteristic. A high viscosity index indicates a small oil viscosity change with temperature. A low viscosity index indicates a large oil viscosity change with temperature. Compressibility is another characteristic of fluids. It measures the change in volume of a fluid as a response to a change in pressure. Fluids, such as gases, are highly compressible. Their volumes change significantly when placed under pressure. Liquid fluids also have a compressibility factor. Water and petroleum-based hydraulic fluid are almost completely incompressible. They don't compress when put under pressure. This characteristic is what allows them to be used to transmit power in fluid systems. Years ago, water was used as the first hydraulic fluid because there was no other liquid available in such large quantities at such a low cost. There are some major drawbacks to using water as a working fluid. Due to its low viscosity, it is difficult to pump. Additionally, the speed at which it flows through the system causes an effect known as wire drawing. Wire drawing occurs when the water flow erodes or scores a pathway in the metal of machinery as it goes around corners and through orifices. It also has corrosive effects on metal machinery. Over time, petroleum-based hydraulic fluids have become much more cost-effective. For starters, it has a lower specific gravity than any other liquid and can be pumped with less power loss. It also lubricates as it works through the system and has little corrosive effects on metal machinery. Flammability is an issue, but with the development of synthetic oils, alternatives to water remain the preferred working fluid.
What is pressure? Pressure is the physical force exerted on an object. Consider an object, on which a force is acting perpendicular to the surface. Pressure is the force applied perpendicular to the surface of an object per unit area. Area is A, force is F, and pressure is P. Pressure is equal to force divided by area. Types of pressure. There are different types of pressure. We will see 5 important types of pressure here. Atmospheric pressure at sea level. Gauge pressure is the pressure above atmosphere. Vacuum pressure is the pressure below atmosphere. Absolute zero, where there is no pressure exist. Absolute pressure is the pressure above absolute zero. Differential pressure is the difference in pressure between two given points. Atmospheric pressure is also called as barometric pressure. Atmospheric pressure is defined as the force per unit area exerted against a surface by the weight of the air above that surface. Pressure at sea level is approximately 1 atm. Pressure has many units. Here is the equivalent pressure in different units. Gauge pressure is the pressure relative to atmosphere. Gauge pressure is used to measure the pressure difference between a system and the surrounding atmosphere. That's why the reading of pressure gauge is showing 0 at atmosphere. Sometimes, the pressure unit is added with G at the end to indicate gauge pressure. However, without G, it is understood as gauge pressure. Pressure below the atmospheric pressure is called as vacuum pressure. Vacuum pressure is also known as negative gauge pressure. Vacuum pressure is usually indicated with negative sign. Perfect vacuum is never possible in practice. It is not observed anywhere in the universe. Even the space will have a very low pressure, which means not completely vacuum. Pressure above absolute zero is called as absolute pressure. You can notice the word absolute is present in the dial of pressure gauge. Absolute pressure is equal to atmospheric pressure plus gauge pressure. Absolute pressure is always indicated with A at the end of pressure unit. Differential pressure is the difference in pressure between two points. Differential pressure is equal to pressure at point 1 minus pressure at point 2. Differential pressure gauge will be connected with high pressure side at one end and low pressure side at another end. The difference between high pressure side and low pressure side will be indicated in gauge.
One method of measuring atmospheric pressure is by using something called a barometer. A barometer is a glass tube that is closed at one end and then filled with a liquid, like mercury, that is chosen specifically because it is non-volatile, which means it does not evaporate but will remain a liquid. The tube is then inverted and placed into a container of that liquid. The atmosphere exerts pressure on the liquid when particles from the atmosphere collide with particles in the liquid. This activity keeps the liquid in the tube at a particular height. So by observing the height of the column of liquid in the tube, we can see how much the atmosphere is pushing down on the liquid. And in doing so, we are measuring atmospheric pressure. In terms of the liquid chosen, if we were to use water, normal atmospheric pressure can support a column of water over 10 meters tall, which is not terribly convenient for storing or taking measurements. For this reason, we decided to use a different liquid. Mercury is much more dense than water, so a mercury barometer will not have to be so tall. In fact, atmospheric pressure will support a column of mercury that is only 760 millimeters tall. And this relationship between the height of a column of mercury in a barometer and atmospheric pressure is where we get the conversion between atmospheres and millimeters of mercury as units of pressure. The pressure exerted by a fluid due to gravity is called hydrostatic pressure, which is represented by P, and is equal to the height of the fluid times the density of the fluid times g, the acceleration due to gravity. In order to support a column of fluid of a particular height, the atmospheric pressure will have to equal the hydrostatic pressure. We can see that this equation will accurately predict the atmospheric pressure necessary to support a column of mercury of a particular height if we plug in some known values. For example, let's calculate the atmospheric pressure required to support a column of mercury with a height of 760 millimeters. The density of mercury is 13.6 grams per centimeter cubed, and the acceleration due to gravity on Earth is 9.81 meters per second squared. So let's solve for P. We will want all our units to agree, so we can plug in the height of the column and convert to meters, then the density converting to kilograms per cubic meter, and then the gravitational acceleration, which, as we said, is in meters over second squared. We will get about 101,000 pascals, which is roughly equal to atmospheric pressure, and therefore corroborates our experimental observation. There is a device that is similar to a barometer, and it is used to measure not atmospheric pressure, but rather the pressure exerted by a gas that is trapped in a container. This is called a manometer. In a manometer, there will be a bulb containing some gas. This connects to a U-shaped tube that will contain some non-volatile liquid, like mercury, and the gas particles in the bulb will push down on the liquid, just the way atmospheric particles push down on the liquid in a barometer. This tube can be closed to the atmosphere, in which case the difference in height between the two arms of the liquid will be equal to the pressure of the gas. This is called a closed-end manometer. There can also be open-end manometers, in which the top of the tube is open to the atmosphere. In this case, the height of the two arms of the liquid will depend on both the pressure of the gas and atmospheric pressure, and the difference in height will be equal to the difference in the two pressures, the one in the bulb and the one outside of the apparatus. We may have to add the height difference to atmospheric pressure or subtract it from atmospheric pressure, depending on which arm is taller, as the gas may be pushing with more force, or the atmosphere may be pushing with more force. Let's say we are looking at a closed-end manometer filled with mercury, and we measure the difference in height as being 26.4 centimeters. We can use this value to express the pressure of the gas that is pushing down on the mercury in a few different units. If we want to use torr, we can just take our value in centimeters of mercury and convert into millimeters of mercury, which we will treat as being equivalent to torr. From torr, we could convert into atmospheres, pascals, or bar. So just by measuring the difference in height of the arms of liquid mercury, we can state in a quantitative way precisely the amount of pressure that a sample of gas exerts in relevant units. Let's say instead we are looking at an open-end manometer. Here we measure the difference in height as being 13.7 centimeters. Assuming this is taking place at sea level, what is the pressure of the gas? This time we have to utilize atmospheric pressure. If the mercury rises higher on the right side, that means that the gas is pushing on it with more pressure than the atmosphere is. So the difference in height of the two arms must be added to atmospheric pressure to get the pressure of the gas. We know atmospheric pressure is 760 millimeters of mercury, so we will take the 137 measured here and add it to 760 to get 897 millimeters mercury. From there, we could convert into any other unit of pressure if we wished. These kinds of devices have an extremely practical application, and that involves measuring the pressure exerted by a gas that is evolving from a chemical reaction. Plotting this pressure over time allows us to do kinetic studies on any reaction that evolves a gaseous product. So between barometers and manometers, we now have a variety of ways to measure the pressure exerted by the atmosphere or an isolated sample of gas.